Fermat's Last Theorem, the geometric proof to an infinite descent. My motto: plain honesty, simple truth, easy understanding, the joy of finding things out for yourself. Starting with the quarter squares rule at the end of the geometric proof video, we backtrack and deconstruct until we arrive at a suitable starting point for this proof. Now b to the n is just b times b to the n minus 1, and the product of two factors is just, well, it's just a rectangle. Furthermore, a to the n is also just a rectangle, a to the power 1 times a to the power n minus 1. As an aside, again the geometry shows that the rate of change of the function x to the n is dy by dx equals nx to the power n minus 1, since the top right hand corner of each and every rectangle sits on the curve x to the n minus 1. Therefore, a to the n minus b to the n is just a to the power n minus 1 minus b to the power n minus 1, all multiplied by b to the power 1, plus a to the power 1 minus b to the power 1, all multiplied by a to the power n minus 1. The difference of two rectangles equal to the sum of two rectangles. Also, a to the n minus b to the n equals a to the n minus 1 minus b to the n minus 1, all multiplied by a to the power 1, plus a to the 1 minus b to the 1, all multiplied by b to the n minus 1. The difference of two rectangles equal to the sum of two rectangles. So we have, in total, the difference of two rectangles equal to the sum of two rectangles in two different ways. Well, no, actually what we do have is we have the difference of two rectangles equal to the sum of two rectangles in n minus 1 ways, as the table there shows. What is not immediately apparent is that for the even powers only, the middle equation is also given by a to the power 2n minus b to the power 2n equals a to the n plus b to the n times a to the n minus b to the n, which replacing n by 1 gives us a squared minus b squared equals a plus b times a minus b, that well-known identity for the difference of two squares, alias Euclid's Elements Book 2, propositions 5 and 6. Well, who'd have thought it? Not only that, but the astute amongst you, which rules out the mathematicians, will have noticed that the first and last equations in the table rearranged to give the following two equations, where we can see that the right-hand sides of the equation have integer divisors a or b. The two ascent equations are changed to two descent equations. Stated more generally, for n greater than x, we have the following two equations where the integer in the exponent has been replaced by x. Thus, from one difference of powers equations, we get all the other difference of powers equations for every exponent less than n, for any and all AB pairs. We have replaced b to the n minus x by c to the n minus x in the above two equations. So what would this mean if a to the n equals b to the n plus c to the n also existed? Does this not imply that the Fermat equation exists at every other lower exponent level? I believe that Pierre de Fermat saw it from a slightly different viewpoint, as shown in the following equations. That is, that all a to the n minus b to the n's could be calculated for the AB pair for every other higher exponent level, all the way to infinity. This is truly descent from infinity, and proof beyond doubt that an all integer a to the n minus b to the n equals c to the n could never ever exist. QED. The following numerical examples clearly demonstrate the simplistic beauty that the equations reveal, enough to make anyone with a mathematical soul cry. I have previously published the following tables, the simple symmetry of which even a 5-year-old could easily understand. Taking the four yellow highlighted entries from the preceding tables, we see that the red-blue integers are just the AB's in the preceding algebraic equations. The equations are the very well known but also equally well ignored binomial numbers. All we have to do is increase the given exponents by 1 and replace the yellow values for the difference of the powers by the preceding answers also in yellow, and we have the differences for the next higher power. Easy peasy. The fundamental numerical derivation starting at the difference of squares for adjacent integers only is as shown. It is only after rearrangement that we get the two equalities that give us the difference of the elevated powers. Where the numbers are not adjacent, we have to take into account the fact that a minus b is not equal to 1 and multiply by it. This is clearly demonstrated in the list of calculations. The extracts from Hall and Knight's 1896 elementary algebra details the algebra responsible for generating the binomial numbers equations. The equations I have produced are just compacted equivalents as shown by the numerical confirmation. As a finale to the video, I want to answer the question, what is 0 to the power 0? Well, if we look at the first entry from my previously published difference of the powers, which I have copied and pasted above, you will see that 0 to the power 0 must be equal to 1. It can be physically demonstrated. So sorry, Prof, but your reasoned argument is wrong, or at least not absolute.